Well, hey there, everybody. Mr. Carlson here, and today we're going to talk about something real exciting. It's called ions. Ions. We're going to learn about what ions are, how they're formed, and then the trends in the periodic table that we see with ions. So, first of all, let's talk about what the heck an ion is. And to do that, we're going to use this example of a lithium atom. So, when we think about lithium, let's go to the periodic table here. Whoa, hold on, right there. There's the periodic table. If we look at lithium, here's lithium right here. We know that lithium has an atomic number of 3, which means it has 3 protons. It also has 3 electrons. And also, remember what we learned the other day, is that lithium is in group 1 here, group 1, which means, remember what that means? That means that lithium, since it's in group 1, it has 1 valence electron. 1 valence electron, right? So let's come back over here, and we're going to draw the full Bohr model here with the energy levels for lithium. So it's got 3 protons, 1, 2, 3. Remember, protons have a positive charge, so I'm going to put a positive charge in each one there. And heck, why not? Let's put some neutrons in there which don't have any charge at all. So there's our nucleus of a lithium atom, and it also has 3 electrons. Now, remember that if we look at where lithium is, so lithium has 3 electrons. 2 of those electrons are in the first energy level. So remember, this would be 1. Whoops, this would be 1 here. First energy level with its 1, 2 electrons that can fit in the first energy level. That's it. Remember, 1, 2 in the s orbital there. So I'm going to come back over here. I'm going to put, here's my first energy level, and it's got 1, 2 electrons. And so that means the third and final electron for lithium out of its 3 electrons, that final one is in this last energy level here, the second energy level, and it has 1 electron there. Now, here's the thing. So here's our atom of lithium. It's got 3 electrons, 3 protons. 2 of its electrons are in the first energy level, 1 electron in the second energy level. Now, here's what we got to remember from the other day when we were talking about valence electrons. So valence electrons, remember we said that that's the final energy level. And to be, let me go back over here actually, to be stable, to be a stable, for an element to be in a stable state or an atom to be in a stable state, what it really wants is it wants to have a full valence shell, or a full outer energy level, okay? And then it will be happy. Like for example, lithium here, it only has 1 electron in this outer shell, but we can fit 8 electrons in that outer shell, right? We can fit 8 electrons in there. It only has 1, and so it has room to fit more in there, and so therefore lithium is actually kind of unstable because it doesn't have a full outer shell. Now, to get a full outer shell, so remember what we said, and we talked about this a little bit last week, is you can fit, and this is for any of these elements, and we're going to skip over, by the way, let's just make a note of this now. We're skipping over these transition elements. We're not going to worry about these right now as far as what we're talking about today. They'll come into play a little later. They have some different rules, but we're not going to worry about those. We're going to just talk about the representative elements here. So these 2 columns and then our nonmetals over here is what we're talking about. But for all of these representative elements, they can fit 8 electrons in their outer shell, except for helium and hydrogen, though, because they only have 1 energy level, right? They only have this 1 energy level, which can only fit 2 electrons. And so if either one of these guys can get 2 electrons in their outer shell, that's a full valence shell for them. But for the most part, for the rest of these guys, it's 8 electrons. So we're going to make a note of that over here, that 8 is the magic number. So 8 electrons. Actually, let's make 8 valence electrons is the magic number here. 8 valence electrons for most elements is a full valence shell. And then we'll say 2 valence electrons for some. 2 valence electrons for some. And in fact, lithium is one of those examples because if we think about this, let's look at this. So lithium is going to have 2 choices here in order to become stable. Right now it's unstable. It doesn't have a full valence shell. It wants to get a full valence shell. So it's got 2 choices. First choice is this. It can try to somehow get 7 more electrons. It's only got 1 here. It can fit 8. So it can try to get 1, 2, 3, 4, 5, 6, 7 more electrons, so it can have a full outer shell of 8. It can try to do that somehow, try to gain 8 more electrons. Or it could, its other option, instead of trying to gain 7, it could try to just get rid of this one. And if it can get rid of that one, then what's going to happen is that this whole shell, this energy level, goes away because it no longer has any electrons, right? So then it's gone and drops back down to this, which is already a full shell, isn't it? So by losing that 1 electron there, it then gets a full outer shell because the one that is below it there already is a full shell. And so that's going to be the easier option. It's going to be a lot easier for lithium to lose that 1 electron instead of trying to gain 7 electrons. And so that's exactly what lithium does. It loses an electron here. Now let's think about this. Let's say, let me read real quick. Let's redraw this in. If I have just a regular standard old lithium atom here that hasn't lost any electrons, so if I have we'll say a neutral lithium atom. The reason why we would say it's a neutral lithium atom is because it has the same amount of negative charges. Remember, electrons are negative. So there's 1, 2, 3 negative charges, and there's 1, 2, 3 positive charges. So therefore, the amount of positive charge and the amount of negative charge that this atom has, they cancel each other out. And so this whole thing actually has no charge at all. It's neutral because these charges balance each other out. It's neutral, and so we would just write lithium, there's the symbol for it, no charge necessary. But if lithium, which it is very eager to do, if it loses this electron, which it really, really wants to do, if it loses that, now it's no longer a neutral lithium atom because it has an imbalance of charges. Because look, now I've got 1, 2, 3 protons. That number hasn't changed, but my amount of electrons has changed. And so now I've only got 1, 2 negative charges. So now I have more positive charges than I do negative charges. And I have 1 more positive charge. I have 1 more positive charge than I do negative charge. And so therefore, when lithium ionizes, we would say, when it loses an electron, it has now become an ion. And so for a lithium ion, that's what the term ion means, something that has a charge, something that either gains or loses electrons and now has an overall charge to it. This lithium ion has lost 1 electron, and so therefore it has a charge. So we'll say loses 1 electron, and now has a charge of positive 1 because it has 1 more positive charge than it does negative charge, and therefore the overall charge of this whole atom, or ion I should say, is positive 1. And so the way we would write that is we would put the symbol lithium, and then what we're going to do is we're going to put a plus up here in the upper right hand corner, Li plus. And when we see that, that means that we have a lithium ion with a charge of plus 1. Let's think about a different element, for example, calcium. Let's do the same thing with calcium. With calcium, if I look, calcium is right here on the periodic table. Calcium, which has 20 protons and 20 electrons. Now let's just look at the valence electrons though. So calcium is in group 2. That means it has 2 valence electrons. So I'm not going to draw the whole model of calcium. All I'm going to do is write the electron dot diagram that we learned in the last video. So remember, dot diagrams show the valence electrons, how many valence electrons it has. So for calcium, it's got 1, 2 valence electrons. Remember, I can fit 8. It only has 2. And so we ask ourselves, is it going to be easier for calcium to lose these 2 electrons? Or is it going to be easier for calcium to try and gain 6 electrons to get a full outer shell? The answer is it's going to be easier for calcium just to try to get rid of these two, because then, again, like this atom of lithium up here, it would drop down to this shell that is already full. And so for calcium, it's going to lose 2. It's going to lose 2 electrons. We're going to get rid of those. And now, calcium, since it's lost 2 electrons, so loses 2 electrons, it now has a charge of +2, because now it has 2 more protons than electrons. And so the pattern we see here is for every electron you lose, that's how much positive charge you get. So if you lose 3 electrons, well, then your charge is going to be +3. If you lose 1 electron, it's +1. You lose 2, it's +2 is the charge that you now have, right? And so this calcium ion has a charge of +2. The way we would write that is we're going to put 2+. All right, 2+. We're going to put the positive sign after the number. Whenever it's a charge of just 1, we don't put 1. We just put either positive or negative. But for 2 or 3 or 4, then what we're going to do is we're going to put the number first and then what the charge is. And again, what this number is saying here, that's the charge. That's the charge. It's not... I think students really get confused sometimes because they say, well, it's losing 2 electrons. It's losing 2, and so what they really want to put here is they want to put Ca -2 because it lost 2 electrons. But you got to be very careful here. This number is saying that you've got 2 more positive charges than negative charges, and so just be aware of that, because it's a very common mistake that students make. So let's take a look at the other side of the periodic table, shall we? So we looked at lithium and we looked at calcium. Let's look at these nonmetals over here, okay, on the other side. So let's take a look at the example of fluorine. Fluorine, which is on this side of the periodic table. So remember that up at the top here, we learned this last week in the last video, that for valence electrons, right, this right here, this 13, we would subtract 10, so there's 3 valence electrons here. 4, 5, 6, 7, and 8 in this group here. So fluorine is in group 17, which has 7 valence electrons. So let's come back over here. We're going to write the electron dot diagram for this. Fluorine, 1, 2, 3, 4, 5, 6, 7. 7 valence electrons for fluorine. Now, we ask ourselves the same question. Is it going to be easier for fluorine to try to gain 1 electron to get a full outer shell of 8? Or is it going to be easier to lose 7? To lose 7 and drop back down to its previous full shell? And the answer in this case, unlike calcium and lithium, it's going to be easier for fluorine to gain an electron instead of losing electrons, right? Because it's so close to already having a full outer shell, it's going to be easier to try to steal an electron from something and get that full shell of 8 valence electrons. And so that's exactly what it does. And so in this case, instead of getting a positive charge, now I have more negative charge, right? Because I haven't changed the amount of protons I have. I've changed how much negative charge I have, and now I have one more negative charge than positive charge. So in this case, fluorine will gains 1 electron and becomes a fluorine ion with a charge of -1, because it's got one more negative charge than positive charges. And so the way we would write that is capital F with the minus up there in the right hand corner. Okay, and so that's what we see. The pattern is over here we see these positively charged ions. So these guys over here in group 2, they form ions that have a charge of +2. These guys in this group here, in group 1, have one valence electron. They typically lose that valence electron, and so they form charges of +1. But then over here, on this side of the periodic table, what we see is that so in group 17 or group 7a, they have 7 valence electrons. It's going to be easier to gain 1 electron, and so these guys, all in this group here, typically have a charge of -1. These guys here, oxygen, sulfur, and selenium, until we hit the metalloids here, but those guys will typically get a charge of -2 because they're at 6, and if they gain 2, they will get 8. So they're going to gain 2 electrons and so have 2 more negative charges. And then nitrogen and phosphorus here are going to gain 3 electrons, right? And so that's the, now remember this column over here, these noble gases, they're not going to gain or lose anything because they already have 8 valence electrons. That's why we call them the noble gases, remember, because they don't need to react with anything to gain or lose electrons. They're already happy with what they've got, and so they don't form charges. Now, right here we get this row here, carbon. Carbon has 4 valence electrons, so it can kind of go either way. Sometimes carbon gains electrons, sometimes it loses electrons. Most of the time it just shares electrons, and so we're not going to worry about a charge. We're not going to worry about a charge here with carbon for now. Just know that sometimes it'll be a positive charge, sometimes it'll be negative, sometimes it won't have any charge. Boron, we'll say, can sometimes go either way as well. So that can sometimes be a special case, but we'll just say for now that that will sometimes form a +3 charge. But again, sometimes that can go either way as well. All right, so that takes care of what an ion is and how ions form in the pattern.